briefly go over this homework. So the first problem, you have 16 different types of flour. Of those, 4 white, 12 are brown. What's the probability of random selecting a single selection, either white or brown? So the probability of white or brown equals the probability of white plus probability of brown. Can you have a white and brown flour in the same selection? No, so they are mutually exclusive, which means the subtract term falls off. Right? So that's the full equation here. Special version of it, given that they're mutually exclusive. So the probability of white, 4 possibilities out of 16, plus 12 out of 16. Notice not just 4, not just 12. 12 plus 4, 16 out of 16, 1.0. 100%. Very straightforward, very easy question to start off.
So on those, are we supposed to put like 100% or 1.1?
I don't care.
Okay, gotcha.
Right? I do want final answers to be converted to decimal points.
Oh, I didn't know that.
That's okay.
You didn't tell me that in the Pacific.
If you get the correct fraction,
Okay.
and presumably if you get the correct fraction, you will then minimize the fraction to the least common denominator.
Okay, gotcha.
Let's put it this way. I am more concerned that you go through this procedurally correctly than you actually put it into the right. I'll be able to tell the formula. Right, so whether it's a fraction or a decimal point, well, I prefer the decimal point because it's the easiest to simply check through and see if you got it right or right, where you got things wrong. I'm more concerned that you get the formulaic interpretation of how these problems set up. Right? The formulas are actually in many ways just as important. You have credit to get the right formula. For the exam, you're going through problems, and I give you a problem, and you say, oh, I don't know how to do this, but I use the addition rule, right? And I use a special case addition rule, or I use a general case addition rule, and here's why. I'll even have credit for it. All right, so it's probably random selecting white flour, and notice the end of the order, the first couple questions are right, underlined. So probability of white and, brown in the second row. That's the probability of white, followed by the probability of brown, given that you already had a white one. Right? But notice at the top it says with replacement. Right? If you do it with replacement, right, that means these are essentially independent events for each other, so you go back to full 16. And so this, with replacement, is probability of white times probability of brown, which in this case is 4 out of 16 times 12 out of 16, which gives you an answer of, I don't know what the exact fractional thing is, but it comes out to be 0.1875 in your decimal point. Next question is very similar, probability of brown and then white. Same basic problem, except you're flipping brown white, which essentially then, 12 out of the 16, scribbling incorrectly. Same answer, because it's with replacement. If it were without replacement, right, it would be 4 out of 16 followed by 12 out of 15. And this would be 12 out of 16 times 4 out of 15, which give you different numbers. But in this case, because it's with replacement, it doesn't matter if you go 1 then 2 or 2 then 1. It's communicated. So it's probability of selecting 3 brown flowers in a row. Notice 3 brown flowers in a row is first brown and second brown and third brown with replacement, probability of brown, followed by probability of brown, followed by probability of brown, which is 12 out of 16 times 12 out of 16 times 12 out of 16, or 12 out of 16 to the third power, right? 3/4 for the third power, 0.75 to the third power, which essentially gives you an answer of 0.4219. But notice when I say first draw, second draw, third draw, 3 in a row, that automatically implies first and second and third. So multiplication rule. Does that make sense? So the first problem is relatively straightforward. Next couple problems get more involved. For the second problem, normal 52 card deck, what's the probability of each of the following? Draw your red card or a 9. So you want the probability of red or 9, which is going to equal the probability of red, additional because you have or, plus probability of 9. You can have a red 9, so they are not mutually exclusive, which means the general case for the probability rules, general case of the addition rule. So probability of red and 9. Plug in values, probability of red, 26 over 52. Probability of 9 is 4 out of 52, minus probability of red and 9, which is 2 out of 52. Which then works out to 28 over 52, which is essentially equal to 0.54. Much like we did in class. An almost exact example of that type of thing in class. That make sense?
But I think I got 0.054.
Then you got off by a decimal point somewhere.
Well, can you just do that? Let's get to this.
Nope, I can't. Probably drawing either a 2 or a 3 or a 5. So slight variation of the addition rule. 2 or 3 or 5. Can I draw simultaneously in the same drawing 2 and a 3?
No.
Can I draw a 2 and a 5? Can I draw a 3 and a 5? No, those numbers are all mutually exclusive from each other, which means this will simplify then down to the simple case of the addition rule. Probability of a 2 plus the probability of a 3 plus the probability of a 5, which in this case is 4 out of 52 plus 4 out of 52 plus 4 out of 52, which is going to give me 12 out of 52, which gives me a value of 0.23. Okay. 3 5s in a row. Three 5s in 3 draws with replacement. Notice with replacement means the draws are independent of each other. You take out a 5, you put it back in, reshuffle. This is going to be multiplication rule. It's probability of 5 and 5 and 5. First draw, second draw, third draw. Right? If it's with replacement, they're independent. So that's the probability of 5 times probability of 5 times probability of 5. With replacement, 4 out of 52 times 4 out of 52 times 4 out of 52, which gives you a value of, well, 0.0000456. It's 4 out of 52 to the third time. Alright? Notice how that problem is different from the one directly underneath it. Well, it's probably 3 5s and 3 draws without replacement. That means our events are not independent, which means the probability of drawing a 5 times the probability of drawing a 5 given, you had a 5 on the first draw, times the probability of a 5 given, you had a 5 on the first draw and a 5 on the second draw, which in this case is 4 out of 52 times, there's 1 5 gone at this point, you didn't replace it, 3, there are only 51 cards left in the deck, right? 5 given you draw on the first 2, there are only 2 5s left in the deck, there are only 50 cards left in the deck. So without replacement, you get this set of things, which is different from one with replacement. And in this case, it turns out to be 0.077 times 0.059 times 0.04, which is going to work out to be 0.00018.
How far do you want us to go in with decimals?
Usually 2 significant figures, which in this case would be the 0.45 or 0.46 to round it, 0.18 there. You definitely want to have, well, the zeros don't count as significant figures in this case. So you want to have 2 full numbers, whatever they happen to be, in each case. There'll be a couple of cases where the numbers may be incredibly small, so you have a series of zeros. But usually zeros in this context do not count as significant figures. You basically want to have the decimal points, you know how many spaces you're into, the tenths, the hundreds, the thousands, the 10,000s stacked together. That make sense? Mainly here's if I see when we use the addition rule versus when we use the multiplication rule. Well, decks of cards tend to be prescribed probabilities. The next one has probabilities you have to actually put into place. So, Stamp Collector has 24 stamps from 1970. So, 1970, 24. 22 from the U.S. So we'll put 22 U.S., 2 Canada. 16 from 1975. And from those in terms of the U.S., 13 US, 3 Canada, and then 10 from 1960. And from those, 7 US, 3 Canada. Total here, right? 50 total stamps. Right, that's going to be important in terms of calculating probabilities. So, the first one was probably randomly select a stamp from 1975. So, this is the block from 1975. There's 16 in 1975, so you just look at a probability of 1975 is equal to 16 out of 50, which at the decimal point is 0.32. Alright, that was pretty easy. Next one was probably random select stamp that is either 1970, notice, or from Canada. So, probability, we'll say 70, or Canada is the probability of 70 plus probability of Canada minus probability of 1970 and Canada. So we have some of the stamps from 1970 and Canada. So the first one was the probability of a stamp from 1970. So there are 24 stamps from 1970. That's 24 out of 50. Plus from Canada, if you look at the total here, there are 8 total stamps from Canada. Right? It's going to give me 8 out of 50. Minus 70 and Canada, that's only this one, which is minus 2 out of 50. Notice the reason it's subtracted again, right? I've already counted the 1970 here, I've counted Canada here, so I take 1 away, which is why the combined term is removed. All right, I've added in the 70 and Canada, once for the 1970, once for the Canada, so I take away once here. When you calculate that, that turns out to be 30 out of 50, which is 0.6. Make sense? And then probably the hardest one on the page. What's probably random selecting? Notice in 3 selections. So we kind of frame this as you want probability of first and second and third. So you're selecting 3 things.
I was telling Cameron that if she's not here, I was telling him that I'm gonna have to remind Cameron that we have a test next week, so she doesn't forget.
You want the first draw and the second draw and the third draw. In which, right, with replacement, so each draw you're putting it back in with replacement. First one, stamp from 1970. So first is 1970. And second draw, 1960. And third draw is either 1970 or US. So this is 1970 or US. So basically it's, well, big picture, multiplication first, second, third draw, but within the third draw, addition rule. So you're mixing up the additional multiplication rules. So going from 19, well, I should say, using the ands, given us with replacement, that's probability of 1970 times probability of 1960 times the probability of 70 or US. This is then going to break down as probability of 1970. I'll get the things put on chair. Plus the probability of US minus probability of 70 and US. So that whole thing is going to go in there. So the probability from 1970 is 24 out of 50. That's the first draw. And second draw, probability of 1960. So 10 out of 50 times, I'll leave the brackets, square brackets. 1970 we just said was 24 out of 50. Plus, from the US, if you count down the US ones there, you've got 42 out of 50. Minus probability of US and 1970, which is US and 1970, which is 2. So that's the way that one sets up. And from there it's just doing the math. When you do the math there, this works out to be like 0.48, this works out to 0.20, this is 0.88 in the brackets. So when you multiply those 3 together, you get a value of correctly 0.0845.
Okay. is the 2 out of 50 supposed to be 22 out of 50, or am I just wrong? It's saying
Stand from 1970 or from the
one
US,
from the US.
right?
What?
This is 1970.
Yeah.
This is US. This is 1970 and US.
1970
and US is 2 out of.
No, that's Canada.
Oh, sorry. 22. You're right.
Okay.
The numbers otherwise should be correct.
Yeah. Okay. Okay.
Yeah, you're right. So I was looking at the wrong one there. You are correct. That should be 22 out of 50. Does that make sense?
Mm-hmm.
Question?
And it is okay if it's like fractions on stone?
I'll accept the fractions as long as I can read them, and you typically try to reduce them. I would prefer them to be in a decimal point because that way I can make sure everybody's doing the same thing, give me the same answer back. Trouble with fractions is any fraction can be represented as multiple different fractions. So 1/2 is the same thing as 2/4, which is the same thing as 3/6, which is the same thing as 5/10, which is the same thing as 1632.
And it was hard
So it's
to
better to put it
reduce them
decimal.
when it got to those big, large numbers. I'm like, what goes into 1,360,000? How many times? So that was pretty hard, so I let that alone go through.
Sometimes it's easier to take the fractions, convert them to decimal points, and multiply the decimal points.
Huh.
Right?
I see what you mean.
It depends on whether,
Multiply the
it
decimal
depends
points
on,
by
for
100.
example, if you're doing the addition rules, you want to keep the same denominator, so you can go across the denominators and add and subtract. But in the multiplication rule, it's sometimes easier to go ahead and convert to decimal points, and then you multiply the decimal points straight across.
Oh.
You can do it either way.
That would make it a lot better because my calculator was.
Yeah, you can do it either way, as
Yeah.
long as you keep it straight. It's sometimes simpler conceptually to work it sometimes as fractions, sometimes as decimal points, sometimes switching back and forth.
Yeah. Because the calculator, it's easier to put in decimals than it is to put in fractions.
If you want to do everything decimals as you go through, do it as decimals going through. Like, but you can convert, say, for example, all these, right?
Yeah.
The 10 would be 0.20 as a fraction. The 16 would be 0.32 as a fraction. The 24 would be 0.48 as a fraction. You can just go straight down to those if you wanted. Use the decimal point notation instead of fractions if you wanted. But sometimes that doesn't quite line up. I think it's sometimes easier using the least common denominator, or at least a common denominator, for the addition problems to use the fractions first and then convert to decimals. If you want to convert to decimals all the way through, you can do that too. Does that make sense?
Mm-hmm.
Alright, so the next problem, deal with candy. Different set of starting probabilities. It says Halloween candy. Is it Halloween candy or is it Easter candy?
Easter.
I'm dealing with alliteration in my.
I said somebody's in the spirit.
Depends on whether my statistics class is in the fall or the spring. Whether I use
That's
Halloween.
funny.
What? Well, it usually falls at this point, either right around
Yeah.
Halloween or right around Easter.
Yeah, that's really cool.
I think the numbers are the same. Let me double check. Yeah, the numbers show the same. So, you have a variety of candies, right? 10 red, 15 green, 25 white. Again, summing to 50. They don't have to sum to 50. You may have other probabilities later in the class, and sort of probably 50 is a nice easy number, right? Of all of them, 14 have crack in them. So 14 cracked. If 14 are cracked and you have 50 total candies, how many do not have cracks?
That is
The rest.
Do you mean that they have crack,
have a crack
in
in
them?
a crack
Or they
in them.
have, yeah, or they have
A crack in them.
in
You
them.
said they have crack in them.
So 30,
I said A.
No,
No,
you
you
didn't. No, you didn't. You said
I may have
crack.
said crack squirrel.
no.
And
I
they're really
think-
good candy.
I think there's some like
How many
subliminal.
don't have cracks in them?
36. Do y'all remember that candy he gave us last semester? Mm-hmm.
Yeah, in
What?
there.
It should be
The
tested.
That one did have crack
For
in
messy
it.
days.
Yeah.
I started to do really well on my tests after that.
Never given anyone illegal recreational drugs in any way.
Without their permission.
Never given anyone illegal recreational drugs
How do
in
we
any
know
way.
it's not part of an experiment and he'll tell us when the experiment's over?
Long
Do
after.
you know
Oh,
what-
God,
have you ever heard of Project MK Ultra?
Well, yeah.
That sounds like a yes.
Pretty scary.
What's that? If you got
Back in
something.
the 1960s, the CIA dosed unsuspecting people with LSD. and they monitored their behaviors.
Legal?
No, it's not
It's
legally.
CIA, come on now.
It was entirely clandestine. Right? It was mostly administered through brothels, though the entire project also incorporated the people at the CIA in terms of the staff,
That's not
secretaries, the employees.
I love it, it's so funny.
Right? So at any given day in the CIA in the 1960s, you might inadvertently be dosed by your superiors with LSD and not know it.
Interesting.
Quick question, I'm sorry,
Huh?
not to get off topic, it's quick. I watched this documentary, right, from my other class, and they said that it was like a twin study. They did a twin study and they illegally separated twins and put them in different families and were in foster care and were tracking them. It was like a Jewish facility or something like that, and they were tracking them or something like that. And it was trying to see how if you put this one in a nice home and this one in a bad. Okay, so anyway, the records were sealed until like hundreds of years later when they died.
Wouldn't be hundreds of years later, but
Well,
hundreds.
many years later when the people who were a part of it died, they do stuff like that,
Not ethically, no.
and it's not
But
illegal.
if it was 100 years, then back in the 1920s, yeah, people did
Yeah,
stuff like
they
that
don't
because there
have-
was no oversight from the scientific community at that time.
And if is it illegal to open the records before they die? Because they were the kids were
I
trying to
don't know
figure out to
the
get their
situation.
okay, like the kids were trying to get their records and the documents and stuff like that because one of them actually killed themselves. One twin actually killed themselves.
I don't
And
know
they
that
said that it
particular
was
study.
illegal to open the documents, but how would it be illegal to open it if something
I have
somebody
no
died?
idea. I imagine it's entirely illegal play on the part of the people who own the records. They
Oh,
don't get
yeah.
the various
I was
information.
invested. I
They
was like, oh
probably
my
told
god.
them it was illegal when it was.
I would imagine that the people involved in whoever owned the records were trying to hide their unethical studies, and so they basically tried to make legal arguments that it was sealed.
Yes,
Okay.
that's what they okay.
Whether or not that passes judicial review, I have no idea.
It was terrible. It was a good documentary.
All right, so notice, big assumption, assume cracked variable is independent of color. So whether it's cracked, it's independent of color, which means being cracked or having a color does not affect each other, right?
Right.
Independence is involved, so if you're doing multiplication problems, it'll be independent. So the first question, what's probably random selecting non-red sweet tart? You can do this two ways. You can just say, what's the probability of red? In which case, probability of red is 10 out of 50, which is going to equal 0.20. Take that number, 1 minus 0.20, and get 0.80. That's non-red, right? Makes sense? Know what the probability of red is? You know that red is mutually exhaustive with non-red, mutually exclusive with non-red, so anything other than red must be non-red. Do it that way. The other way to do it, you recognize probability of not red means either probability of green or white. Green and white are also mutually exclusive. So probability of green is 15 out of 50 plus the probability of white, which is 25 out of 50, which gives you 40 out of 50, which is the same thing, 0.80. Right? Either way works. Right? One way uses the subtraction starts with red, one way uses the addition rule, so you can use it white. Right? That makes sense? That one's an easy one. Let's probably select from the bag a cracked green sweet tart. So you want probability of cracked and green. Notice because color is independent from cracked status. Should I just say drug status? Does that mean probability of cracked times probability of green? Probability of cracked is 36 out of 50. Probability of green, oops, 15.
Yeah, I was like,
So that's a 15 out of 50. You multiply those together, you get 0.084.
Wait, why did you do 36 out of 50?
because I
No,
did
it's 14.
15
Oh,
out
sorry,
of 50 and 14.
Cracked, not uncracked.
Okay.
So that should be 14, cracked. That's what I'm
I
there.
was like, I'm doing so good.
So cracked is 14. If it were uncracked, it'd be 36.
Okay.
That makes sense?
Jinx, you love me.
Probably selected from the bag green sweet tart. Then, then replacing it, selecting a white sweet tart. So probability is probability of green and probability of white, first and second. It's with replacement.
So you putting it back.
So you put it back.
Why is that so hard for me to grab? I got it, but I'm just like, my brain just don't think that. But I have to make it.
Probability of green times probability of white, which in this case is 15 out of 50 times 25 out of 50, which gives you a value of 0.15. Okay? Next one I think is a fun problem. Probability of selecting from the bag. Uncracked green,
15,
eaten,
25.
uncracked red, eaten, right? Followed by cracked white, right? Notice if you're eating them, are you replacing them to the bag?
No.
No,
They
so
don't.
without replacement, right?
Mm-hmm.
Notice also you got 3 draws. So you have the probability of, on the first draw,
Sweet.
uncracked, I'll say uncracked comma green, oops, green, and on the second draw, uncracked comma red, and on the third draw, cracked and white.
There was a lot going on. You
If
give
it's
us a-
uncracked green,
Yeah.
that is effectively uncracked and simultaneously green.
Yep.
And so this one becomes probability of uncracked and green, and probability of uncracked and red, and probability of cracked, oops, probability of cracked, and white. So you have 3 draws. We have the multiplication rule nested within the multiplication rule at each one. Right? Not just a matter of putting the probabilities. So the first one is, what's the probability of uncracked and green? Nothing's been drawn at this point. Uncracked is 36 out of 50. And is multiplying. Green is still 15 out of 50. That's the first draw. But now there's one left, one taken out of the bag.
Yep.
Which means when I go to uncracked and red, first of all, how many uncracked ones are in the bag? If I just say
35.
uncracked one,
35.
35. So second draw is 35 divided by
49
49.
times 10
There are 10 red ones, I haven't eaten any red ones yet.
over 49.
But there's still
right?
49 in the bag because that's the second
Okay,
draw,
gotcha.
right? This does not, well, I should say watch your pattern. This does not go 50, 49, 48, 47, 40. It doesn't work like that, right? Think in terms
Okay.
of draws. Think in terms of number of objects selected from the total. So there's 1 in the first draw, that's both of them have denominators of 50. 1 in the second draw, those both have denominators of 49. And then 1 in the third draw, which have denominators of 48. So the 48, cracked and white. How many cracked ones are still in the bag?
14.
All of them, 14.
Mm-hmm.
But at this point, there's only 48 left.
Mm-hmm. And
And they're total
25.
for all the white ones are there.
25.
So it sets up like that. First draw, second draw, third draw.
And then do you multiply them all or do you add? You multiply them, right?
They're all multiplied all the way across this one because this is and is multiplied.
Okay.
Or
What did you?
it will be added.
Can you tell us what the denominator and the numerator are? What you got after you multiply them?
I converted decimal points. This point is multiplied decimal points.
Ah. Darn it.
So no, I did not do the denominator numerator across that.
That's
That will give you a really large number.
why I was like, oh my god.
And I have a really
If
large
you convert
number.
to decimal points, this is 0.30 times 0.72. This one turns out to be 0.2041 times 0.7959.5208
Let me do my decimal.
and 0.2917. When you multiply all those across, you get 0.00533
That is not.
or 0.0049.
Okay, I got that.
Some people may have gotten to 0048, depending on where you rounded it. But it's basically close to a 0.5. 0.05.
Okay.
When
Hair
I-
below.
When I divide my very large fraction, I get 0.0047.
That's from the ballpark.
But it's a big large. Are you gonna be able to know? Like, are you gonna know that?
Just give me the decimal point.
Well,
It's on.
she put the
I
fraction
put
on
the
there.
fraction instead. But the fraction I just did.
Here's what I'm looking for. I'm looking for, did you set it up this way?
Okay.
I did.
Right? If you set it this way, right? Should be a final answer to it, but I'm looking for, did the formula set up correctly in terms of, do you know how to nest the multiplication rule within the multiplication rule?
I don't need no minus ones. My homework depends on my grade.
Yeah, for real.
I need like a 99 test grade.
Alright, so the last couple problems are gonna deal with z-scores. Still probabilities though. I'll point out still probabilities because the end result's gonna be some
Look both
probability
ways before you
of the
press
outcome.
keys.
So last couple problems. Assume average is 14 with a standard deviation of 2.5. So you're given that information. Watch for that kind of information when you do these problems, because frequently that'll be embedded in the very, very introductory kind of, just gonna make like one line. Here's some populations. In order to solve the z-score problems, in this context, especially the next one you're dealing with sampling distribution of the mean, you will be given population mean and population standard deviation, right? So the question is, what's probably a single cell surviving more than 18? Single cell will be X, 18, you draw it. There's the 14, there's the 18, you're looking for this area. 18 minus 14 divided by 2.5 with a z-score gives you a z-score value of 0.16, sorry, 1.6, which means this area is 0.0548 when you look it up. All right, so here's the z-score, that's not a probability, that's a z-score. You look up in the table, the C column, because you want more than 18, that becomes 0.0548.
So on the test, are you usually looking at that or the whole thing? Like the graph too?
I am looking for it. Do you know how to calculate it? Can you come up with the final answer? I would prefer that you draw it. Usually I'll say, draw this distribution.
I hate that.
It doesn't have to be perfect. You just throw in a couple numbers like it there. It looks like a little curve. Throw numbers where they are representative. Figure out which area you're looking at. Because that helps you shade the appropriate area. Okay? The single biggest problem most people make in this area is they try to do the math and they don't know what they're looking at because they don't know where it's visualized. Right? More than, less than, between kind of stuff. So second problem, it's probably a single cell. Notice single cells surviving less than 8 days. There's your distribution. There's your 8. You're looking for this area. Well, do it the other way. You're gonna have negative number for z-score. Z-score is going to equal a negative 2.4, which is going to be, put a negative 2.4 there, 0 there. This area then associated with 2.4 becomes 0.0082. Right? And the third one's probably a single cell surviving between 8 and 18. You just did the math. There's the 0.16. Here's the negative 2.4. 14 there, 8 there, 18 up here, negative 2.4, 1.6. You now want that area between them, right? And so you take the 0.50 minus the 0.548, you take the 0.50 minus the 0.082, add them together, right? Or you can just take the B columns. The B columns were 0.4918 and 0.4452. When you add those together, you get a value of 0.9370.
How we got
Does that make sense?
Yeah.
All right, so number 6 then on the question sheet is dealing with the sampling distribution. This problem, notice in each case said what's probably drawing a single score, single value. The next problem is what's probably going to select a group of 15 that have an average of 16. So now in addition to having the average for the here, you're going to have an average for the sample, right? And you're going to have a sample size, right? Given those 4 values, mean for the population, mean for a sample, standard deviation for a population, number of scores in the sample, right? That's going to set up as a z-score for the sampling distribution of the mean, x bar minus mu over standard deviation over the square root of n, okay? So the first one, that question is what's probability surviving 15 cells surviving 16 or more. So 14 is population average, you want 16 or more, right? But now 16 is not a single score, 16 is an average for the sample, so the z is going to set up as x bar minus mu divided by standard deviation over the square root of n. You're going to set up then as 16 minus 14 over 2.5 divided by the square root of 15. All right, well, 15 is the sample size. When you use the z-score there, this little value turns out, well, the z-score for it turns out to be 3.08, which means this value is now 0.0010. Right? Make a point here, even though I actually erased it. Actually, yeah, I erased it. Well, I know here. The 18 here, right, at about a 5% or so in this little area. 16's closer to the middle, but that's not a single score from 16. That's 15 scores grouped together as an average of 16. And that probability is even lower, right? It's incredibly low probability. Does that kind of make sense? As you get further and further away from the middle, right, the sample size matters, right? And the more that's, well, the higher the number of n, right, the less you need to go away from the middle to get a very small probability change. Question?
Yes, I'm making sure I'm tracking. So when I did the standard deviation divided by the square root of n, so it was 2.5 divided by square root of 15 and got 0.645, and then I did 16 minus 14 divided by 0.645.
You didn't divide 16 by 14, you subtract 14.
I subtracted that, yeah, I subtracted 16 minus 14 and divided that by 0.645 and got 3.10.
I rounded it already to 0.65. So you, 3.10, if you did the math correct, it's within the ballpark, that's 200ths off, right? 3.10 compared to 3.08, that's the same number.
It was
As
just
long as you
easy.
set it up conceptually in this way, the same way, you're fine. Right? There is a little bit of rounding error depending on exactly where your calculator rounds decimals off. Right?
Okay,
Say 3.10 is pretty much effectively the same thing as 3.08, which is pretty much effectively the same thing as 3.11, which is effectively the same thing as 3.09, which is effectively the same thing as 3.095. It's all the same
It
number.
was just easier on my calculator to do that bottom part first.
That's okay. So, group of cells, in this case, 25 cells, 9 or less. So there's my 9, I want less than 9, right? Same sampling distribution of the mean, so 9 minus the 14, standard deviation still at 2.5, square root of 25, right? Square root of 25 is 5, 2.5 out of 5. Basically, the answer here turns out to be a negative 10. That's a z-score. Huh? It's a negative 10.
You probably will.
Mainly because the 25 is so big, right, compared to the separation between this value, right, doesn't actually appear in your table. Best thing you can say directly from the table, though, is what? Probability here is going to be less than 0.00003, because the smallest value you got for the z-score is a negative 4, right? On the bottom right-hand corner of the z-score distribution. So you can say there is it's less than that value, which is an incredibly small. It'd actually be more like 0.00000. There'd be about 8 or 10 zeros there. 1. That'd be a really, really tiny value. So this layer is really, really small. Because getting 25 scores as with an average of 9, that's really low below population average. And then the next one, what's probably selecting a group of 8 cells, average lifespan between 12 and 16. Well, 16. This one actually sets up relatively neatly if you notice the symmetry of it. First one would be 16 minus 14 over 2.5 divided by the square root of 8, which in this case gives you a z-score of 2.27 within rounding here. If you do the 12 minus the 14, divided by the same things, right? You get a negative 2.27. Right, when you have the 12 minus the 14 over the 2.5 divided by the square root of 8. And you recognize, hey, those two values are symmetrical. Right? They'll have the exact same B area. The B area for both is 0.4884. So you add them together, you get a 0.9768. Does that make sense? Questions on this homework? You will have to do similar problems for the exam next week. In terms of above, below, between, in terms of using single scores as z-scores compared to groups of scores as samples drawn from a sampling distribution of the mean.
So the test's gonna be almost identical as the homework?
It'll be similar to setup, yeah.
especially like the first part.
It'd be very similar to this set. Got it?
Yeah.
All right, so at this point, in terms of the probability stuff, you need to know.
You might see z-scores, looking at a single score compared to a sample, mean standard deviation. You might see z-scores, single score compared to population mean divided by standard deviation. That's a single score. You might see sampling distribution of mean problems, which I'm just doing there. Notice this is also equal to
So this is the exact same thing as that, right? Where the denominator, the standard deviation of the sampling distribution, which is subscript, is equal to standard deviation of population divided by the square root of n. You'll see all four of those formulas.
But the last two are the same thing.
These two are the exact same formula, right? The subscript is telling you this is the standard deviation of the sampling distribution. This is the population mean of the sampling distribution. But the population of the sampling distribution equals the population mean, and the standard deviation of the sampling distribution equals the standard deviation of the population divided by the square root of n.
So we can use either formula.
Yep. For this one, yeah. Those are in fact equal. Okay. We also then, last week, started to the addition rule. General case, if events are mutually exclusive, looks like that, because the A and the B become zero in the mutually exclusive case. And multiplication rule, general case for multiplication rule, followed by the specific case if A and B are independent. So if A and B are independent, the B given A is equal to B, because probability of A doesn't affect B.
Can you do us a favor and write next to each one of the top ones, like I guess when to use that formula or keywords to look at so I can study it?
How's that?
Thank you.
Comparing a single score against a sample set of scores for the first z-score. You're comparing a single score against a population set of scores, if you have population data. You're comparing a sample against population data. The sample will have a size of n, in addition to having a sample mean, you already know the population mean. You may have to calculate the sample mean. If I give you a sample set of raw scores, you may have to calculate standard deviation for S or for sigma. We've already done that in the second example.
We might have to calculate what?
S, standard deviation there. We've already seen it as,
Oh God.
you've seen it,
But it's not cumulative, so why would we be doing it?
because you've already done it. And it is cumulative in the sense the math builds. Right?
So you gonna give us that formula too?
Sure, if you want. I typically don't understand, because you don't really, usually I just go to basic order.
No,
But
you should really.
the
think
possibility
about
is
doing
there,
it.
that you might.
Do we need that? Are we gonna have to use that
That's
formula?
what you said.
Sigma there is sigma here and here. Right? We've already calculated standard deviation for both sample and for population. Both sigma and S show up in the z-score calculations, both in terms of the original z-score calculations for single scores and for the sampling distribution of the mean.
Yeah.
So she's saying, are you gonna make us?
Are you gonna give us the standard deviation, or are we gonna have to calculate it? We're not gonna have to calculate it because we don't have a set of scores, are we?
I probably limit it to given data for.
Is that our last quiz?
No.
Our last test?
No, the final.
Oh, next week is?
No,
Oh,
next
there'll
week
be
is
a
the third test, and there will be a final during the final week.
But it's not cumulative.
Not
Apparently.
literally.
The math
Well,
builds.
yeah.
You,
The
you
math
must know,
builds.
if you don't know what a summation is at this point, right? You must know what a summation is at this point.
Yes, I do.
But I'm not gonna go back and say, what's the
Well, I'm not
summation of
saying-
scores, 1 to 6?
Right. The only reason I was asking is because you said you don't normally give that one, so I was just thinking if you don't normally give
Odds are I will give you the basic information in terms of the population mean, the
Yeah.
sample mean,
Cool.
the sample standard deviation, so.
Towards the end of the test, I think I got 0 on one of my answers.
I'd have to look at it, it's been a couple weeks.
No, I mean, not the test, but the homework.
There was one of the answers which was incredibly close to 0, but there is an actual number associated with it that was not on your table. The second one answer.
On our homework that we just did, I got 0 on, like,
The probability out of the 25, with a sample of 25, drawing a score less than average of 9 for that
if we
sample.
put 0, will that count?
No, it's actually slightly higher than 0. It must be higher than 0.
Or
There
I
is
got
a
0.
probability, but the probability is incredibly small,
Yeah, it's,
almost infinitesimally small.
whoa.
But it's still there because the point of that problem is the z-score distribution
Yeah, I got
is
0.
infinite.
Hmm.
The calculator got that far, but yeah, the z-score distribution is infinite, and the z-score distribution is asymptotic to the x-axis.
Okay.
So there is a value there. The nearest you can figure it out is less than 0.00003, because that's the last number on the
Or what is the
z-score
probability of randomly selecting a group of 25 cells
that have 9 days or less.
that have 9 days or less?
Yes, that one's not 0. It's
Yeah.
very close to 0,
Okay,
but not.
got you. Yeah, I put 0.
All right, so those are the